It's possibly not nuclear, right? And so, and my goal will be, of course, to show you that it probably is nuclear. Okay, so hit me with something.
Solar.
Yes, sir.
Nuclear energy, it's so compact that it's not even nuclear.
Nuclear energy that's so compact that it's not. Well, okay, that one. No, come on. Solar energy is energy from the sun. Yes? Solar energy, listen please. Solar energy is energy from the sun. In the core of the sun, hydrogen is turning into helium. It takes, by the way, 10,000 years for a photon generated in the core of the sun to diffuse. It sort of diffuses out. The sun is made of plasma, so it's opaque to light. Light can't travel freely, so it diffuses as a particle, and then 8 minutes later, after 10,000 years, right, it strikes the Earth. And so solar energy is, it's in fact nuclear energy. Yes, sir? Hydroelectric is the energy of falling water. Yes? Okay. And the water got into the mountains because rain rained it up there. And it evaporated from the seas because the sun shone on the seas. And the sun is a nuclear reactor. Come on. Yes, sir?
Just electricity.
Electricity in this region comes from hydroelectric. But let's suppose it comes from wind power. Yes? Okay, wind power is caused. Wind comes from wind. Wind comes from the uneven heating of the Earth's surface by the sun. Okay, come on. Yes? Ground in the center of the Earth is hot. It is in a state of igneous fusion. Yes? Okay, why is it still hot? It's been 4.5 billion years since its formation. This is not the heat of formation. In fact, this was a mystery. When Darwin came up with his theory of evolution, evolution requires certainly more than thousands of years to occur, right? Yet, I think Kelvin figured out that the Earth had been formed as a molten hot state, right? And everybody would agree that it's molten hot because of its formation, right? It would have cooled in like thousands of years it would take to cool, right? And so the core of the Earth is kept hot because right now there's radioactive things like uranium and thorium and stuff like that are undergoing radioactive decay. So at the core of the Earth, matter is being turned into energy through radioactive nuclear processes. So the Earth itself is a nuclear reactor. Aya's got something. Sound energy. The sound you are hearing comes from me. I ate Wheaties. Wheaties sat under the sun. The sun is a nuclear reactor. Come on. Yes.
The energy it takes me to push a box across the table.
Well, that comes from you. And you ate, what did you eat? Wheaties? I bet you did. And Wheaties get their energy from wheat. Wheat gets its energy from the sun. Come on.
What if you ate
Yeah.
Fuel cells.
Fuel cells. Well, let's see. A fuel cell that uses like hydrogen and oxygen is a typical one, right? Probably we used electricity to make the hydrogen and oxygen, right? So, yada, yada, yeah. Elastic. So like the energy of a stretched spring. Well, who stretched the spring? Probably a person who ate wheat. Yeah? A machine. Yeah. Something falling like a rock on top of a mountain falling. Well, Mount Hood, okay, right now the Pacific plate is subducting. Here's the North American plate. The Pacific plate is subducting. When it gets down low enough in the Earth's core, right, it melts and it comes up, and this is a subduction or something like that. So these volcanoes are actually the sort of frothy stuff that's melted off the Pacific plate, right? And so the powerful tectonic forces deep within the Earth put that rock high on the mountain, right? And so therefore those are from the nuclear forces that are driving tectonics. Yes? Magnets. How do they work? I don't want to ask no scientist. He's all lying and making me angry. I think has anybody seen the ICP miracles?
Yeah.
Magnets. Yeah. So magnets, you would have to make magnets. We would use energy like electrical energy to make them, et cetera, et cetera. Anyway, the point is not necessarily that nuclear energy is the end all be all. It's just a big source of energy. Yes, sir. He's got something. Of thought, yeah, or music, right, or something like that. Well, your thought energy comes from the food you eat or something like that, right? The only thing that people have thought of that's possibly like not nuclear is like the kinetic energy of the moon. And it's like, well, where did that come from? Well, that came from sort of the happenstance of the collapse of some nebula, which came from the Big Bang or something like that. And the Big Bang is pre-nuclear, so nuclei didn't exist for some period of time. But anyway, that's that. Yeah.
An ice block being pushed across another ice block.
Yeah, but you're pushing it, right?
No, like it's sliding by itself.
By itself, like with.
Because it's melting.
No, because it's in Antarctica. Yeah.
Because how did it get there, right? So the point of this whole exercise, boys and girls, is not necessarily about nuclear energy, but just that energy moves around. Yes, energy transforms from one thing to another thing to another thing. right? Nobody, by the way, brought up gasoline.
Gasoline.
Gasoline energy, right? So this is, and I've, I know quite a bit about this. Gasoline comes from the greasy noses of dinosaurs, right? They all fall in a big pile, right? And then rocks are like laid down on top of them, and all that oil gets squeezed out of their noses. I'm a little sketchy on my geology, right? And the dinosaurs got their nose grease from eating plants, right? And plants grew under the sun. But anyway, okay, back to this. Are we ready for this? Okay, so conservation of energy, and this is what we're going to use to solve our stuff next time. When you look at those videos for next time, there's only 4 of them. Look at all the examples, because I really can't explain it without solving a problem. It's very hard to teach, and we're going to spend a lot of it. It's much harder than the stuff we did today. Okay? What conservation of energy states is that if you have a closed system, okay, its energy remains constant. That energy is conserved. Okay? So if this bowling ball is our system, we could say that this is 0 potential energy, right? If we ignore the fact that it's like above the floor, if we say that's height equals 0, right? If we ignore the fact that it's moving because the Earth is rotating and moving through space and all that stuff, we could say it has 0 kinetic energy. If we ignore the thermal energy it possesses, right? There's no springs wound up on it. We could say its total energy is 0, yeah? Couldn't we? Right? And now if I push on it, if I do work on it, it gains energy. This is, by the way, called the work energy theorem. And last night when you're looking at those videos, didn't I always start with force times distance to make energy formulas? Yes. And that's because if you do work on a system, it gains an energy equal to the amount of work you did. Yes? Okay. Now, you know it has energy. What kind of energy does it have? It has potential. When I pushed it to the side, it actually raised itself up. And in fact, if you had to figure out how much work I did, you'd be hard-pressed to do it without calculus, because at first, the force I'm exerting is small, and as I push it to the side, it gets more and more. It's a bit like a spring, only it's actually like some sine function or something, right? So let's suppose, so basically the amount of work I did, if you had to calculate it, you would actually use the MGH to do that, okay? Now, let's suppose I did 10 joules of work. This is how these problems work, right? Let's suppose this is 10 joules of potential energy. If I let it go, and we look at it at the very bottom, okay, freeze frame, it has no potential. If it had 10 joules of potential there, and it has no potential, how much kinetic does it have now? Well, it's got all 10. It's all kinetic, right? How about if we, let's start again. It swings, and we stop it, not at the bottom, but here, where it's got 2 joules of potential. How much kinetic does it have? 8. It always adds to 10, right? That's what conservation of energy says. Let's do another example. You guys are so good. Maybe that was an accident, though. Okay, let's try 7 joules of potential. It's got 3 of kinetic. It always adds to what it was before. So if it started out with 10, it's always going to have 10 total joules of energy. Does that make sense? Now, your English teachers and stuff will just say stuff, right? But very rarely do English teachers put their lives on the line. Okay, so we've come down to sort of a serious part of the period here, okay, where I'm going to put my life on the line. I believe in conservation of energy so much that I'm willing to die if energy is not conserved. Okay? Now, to frame this properly, let's suppose that you're in a situation where you've got to kill somebody with one blow. Sometimes those situations come up, right? With our bare hands, how would one kill somebody, dispatch them efficiently? She's got it. Go for it. How does it work? What do you do? What is it?
You use their own force against them.
Their own force against them. Well, no, that's not what I'm looking for here. Okay, it's good though. It's a good thing. Oh, there it is. There it is. There it is. She looks like this innocent girl, up in the front of the room working on her little thing, but she's a killer, right? Okay, it's the nose, and how do you hit them? How do you hit them? Yeah, it's this, right? Oh, this, you could do that too. I think that would, right? The notion is that, how does it work?
You hit them and the nose bone goes in your brain.
The bone of their nose goes in their brain. What a way to go. Wouldn't you much rather die like in some wild backcountry skiing accident than have the bone of your nose stuffed into your brain if you've got to go, right? Okay, but anyway, here it is. What I'm going to do, and you probably guessed this, okay, is I've got the television set there, so there's no backing out of this, okay? The television set will provide, so if energy is not conserved, I'll release it, it'll come back. If energy is conserved, it should come back to the same height, correct? Okay, but if it's not, it could maybe come lower, and then 50-50 chance it could be a little bit higher, right? Now, I don't know, if the butt of her hand or her fist would knock that bone into my brain, but I'm pretty sure a bowling ball named Artie would do the job.